I can pick an exponentiate a vector, and I can take it in a kind of canonical form. But I don't think that argument straightforward leads me to any computation I want to do, because we were discussing. I take something in the algebra that is a skew symmetric matrix, m by m, and I have to mod out the isotropy, so I have the skew symmetric of that of E times B size and the ones of Q times Q size. So if I mod those out, I will have a matrix that has two rectangular E times Q entries. And then I have to take the exponential, usual matrix exponential of that. And that is not
okay, yes, I understand. You can simplify that computation. So the problem was you take the Grassmannian k-planes in Rn. So this was SON divided by SOK, SON minus k. So then you write down the D, I just call this G mod H. Right? So H was then the diagonal matrices, the block matrices, star 0, 0, star. That's this group right here. And then the complement P was things which have zeros on the diagonal here X, and here minus X transpose. Okay. And then the theorem was that if I take X in P, then XPX times the foot point, so times A, is a geodesic in G mod H. So that was a theorem, right? So now I can simplify as follows. I claim that, and of course, how did the group H acts? So capital H, say. So I want to use the action of H on P to simplify. So H acts on P via, so an element in here, so the form A comma B. These are orthogonal matrices. And on X, this gives me AX B transpose. And X is now, so this is what, K n minus K. So X here is a K n minus K matrix. And let's assume that, see, K, which one do I want to do? There are more columns than rows. So K smaller than n minus K. But of course, these two I can change, right? It's just the orthogonal complement of the plane if I want to. So I might assume this is this. So I have more columns than rows in this picture. And I claim there exists an H in H such that at H applied to X has a normal form. A1 up to AK. Everything else 0. Right, so here I can multiply with arbitrary orthogonal matrices on the left and on the right. And it's not hard to see that everything can be brought into that normal form via some action. So I might as well assume that my vector looks like this, right? Because H acts via symmetries. So if I understand the geodesics, whose image of this here as a geodesic, understand all of them via symmetry. And now to understand this, so now I have to take the exponential, like you said, of this kind of matrix. Now, of course, here then minus A1 minus AK. And that's much easier now. Now I can break it up, right? So like in the first column and in these two rows and columns, there's only A1 and minus A1. If you want to, I can, okay, yeah, that's probably, and E to that is the rotation matrix. Cosine T A1, sine T A1 minus, well, minus sine T, doesn't matter. sine t a1 cosine t a1. So rotation by t times a1. Okay. So, okay. Then what now to apply this to the foot point? So this is my exponential. So I do this in each coordinate, right? So in this first coordinate, it's a rotation, and in the second corresponding coordinate, it's also a rotation. So what's a foot point? Let's see how I want to do that. Well, so as a foot point, I take a plane, right here. This is with respect to some plane that's fixed by h. And what plane is that? The first k vectors, right? So my h here corresponds to E1 up to Ek, the span of that. Okay. Now I have to apply a matrix to that. Right? So now take this matrix here and apply to EI. This will give me a vector, and then take the span of that. So what is this? So apply this matrix to the ith vector. I would get cosine t EI plus sine t, which coordinate is k plus 1, right? Ek plus 1. And now xt, x for this partition, right? Y, say, for this partition. Y is the span of those. I can now express this abstractly. So what does the geodesic in the Grassmannian look like? So geodesic in the Grassmannian. I take a plane, so let P be a plane. Then I can choose a basis. E1 up to Ek, Ek plus 1 up to En, orthonormal basis. And then anything on that form over there, the path, gamma of t, is cosine t E1 plus sine t Ek plus 1, and so on, is a geodesic in the Grassmannian. And I claim I have freedom of choice. What freedom of choice do I have? So this here, of course, is supposed to be, P is supposed to be the span of those first k vectors. I can then choose my complementary base anywhere I want to. Right? That kind of corresponds to in what direction do I want to go here. So that I start rotating. So I take a vector in my plane and rotate in the direction of a vector orthogonal to that plane. Take another vector, rotate in the direction orthogonal to that plane. And if you count the possible choices you can make here, it's besides the dimension of the Grassmannian.
So the action by H, is that choice complement or you just
It's a change of basis here and the change of basis here. So I've now expressed it. That's what at is, right? At H brings it to some kind of normal form here. It's kind of like a choice of the orthonormal basis, a different choice of orthonormal basis where the matrix has this form. And then I can easily see what happens. And now step back a little bit. What does it mean? Well, choose any basis here and any basis here, not just the canonical one. Right? And then this would be geodesic. That's what applying at H would do here. Would take your canonical basis into some other basis.
You also have some dimension coming from the different velocities.
Correct. Okay, sure. So I forgot the AIs here, right? Absolutely. The AIs are velocities with which I rotate in the various coordinates. That's important. Okay. From this description, you can also, for example, figure out what are the cut points, what are the conjugate points. Right? Every geodesic looks like this, and you can see when do they meet again, when something is not minimizing. So I have a very nice explicit description of the geodesic where I can study exactly what happens. So that's what you. So this theorem here, you have to translate into something more geometric, where you can see what's going on, and that's the geometric statement. Okay. So one has to use this trick here that I bring it into some kind of standard normal form where I can exponentiate. Otherwise, it's too complicated. Okay. Any other questions? Okay, so then I promised to do some topology of symmetric. Yes?
Only one more question. In that last exercise that's not on the list, that formula that relates with J and the answer, there is an easier way to see how this formula works, because you can expand and expand and expand.
Gets very complicated?
Yeah. It depends on the way you see the formula. I didn't see very well.
Did someone finish that? No.
I tried to do, but I don't know what to do. And I can expand.
I thought it was just straightforward plugging and expanding, so it gets very complicated. Then I have to take a look at it, whether there's some tricks where you can simplify it.
Yeah, if I write any covariant derivatives, there are 3 terms. There's a lot of terms if you expand.
Because the only property of the coherent derivative you probably need there is that it's torsion-free, right? So this property that nabla xy is minus nabla yx is a real bracket xy. This must be what makes it work, right? There shouldn't be too many terms. But I have to write down and just crank it out and see what happens.
Yeah, I tried.
But too long.
Yeah.
Okay.
Yeah, probably there's a smart way to.
Some trick. Okay. I'll take a look at it. If I can figure out an easy way of doing it, I'll put it on the solutions. I'll post solutions to the exam again at some point. Not sure exactly when, because I have to leave to Germany on Wednesday, but I'll see how quickly I can grade and put the solutions on the homepage. Maybe I'll put this problem on the homepage too then. Okay. Okay, so the RAM cohomology of symmetric spaces, that's the topic. It's a very simple expression. The easy spaces for which one can compute the RAM cohomology. But first I want to do some kind of general discussion, which is quite useful, which works for any manifold on which a Lie group G acts on M. No metric right now, doesn't have to be isometry, it's just a Lie group action. Okay. And I want to assume that G is compact. So I have a compact Lie group acting on a manifold M. I don't need that M is compact at the moment, so just some Lie group acting. Could also be a discrete group even. So this applies also in a very general setup. So then I can introduce, say, a volume form. Which I call dg, which is bi-invariant, as we've done many times before. Now normalize so that the integral dg over the Lie group G is equal to 1. So normalize it so the Lie group has volume 1. Then I can define an averaging operator from the forms. So I'll use this standard notation for forms, right? This set of K forms on the manifold. Into K forms that are called G invariant. So obvious definition, right? Omega is a K form such that G star omega is equal to omega. So that's what I mean by G invariant. So it's a certain subset of forms by just averaging. Right? So I take omega to the integral of of G star omega dg over the Lie group G. And this is my definition of the averaging of omega. And this average procedure has several properties. See in which order I want to write them. First, it commutes with exterior derivative. Right, because so I can bring the d inside, right? So this here would be d of the integral g star omega. Integrals and exterior derivative forms are interchangeable. And of course also d is natural under pullback. So that's the integral of g star of d omega. And that's the average of d omega. So d of the average is the average of d. Okay. So maybe that's the only thing I want to state right now as a general property. And this now has the following consequences. So I can look at a okay, and the next observation is that maybe another one, that if omega is G invariant, this implies that d omega is also G invariant. So if we look at the subset of G invariant ones, then of course I should make the remark, maybe I didn't make this, is I'm averaging over G, that becomes a G invariant form. The usual kind of way that we do this. The average is G invariant. But if I have something that's G invariant already, then I claim d omega is also G invariant. Again, clear, because G star d omega is d of G star omega. So if omega is G invariant, that's the same thing as d omega, which means that d is also G invariant. So that's also clear. So this now implies the following. So under the setup, G acts on M, G is compact. I look at the inclusion of the G invariant forms together with its differential exterior derivative. That's a complex. And I can send that into the set of all forms with the usual differential. And I get an induced map in the homology of this complex, if you want to. So let's write it. So this, of course, here is, as usual, kernel D divided by image D. But now restricted only to G invariant forms. Right? And here I do the same thing. And of course, if I take the cohomology of this complex, I get what you call the Ram cohomology. And the claim is that this is an isomorphism. Sorry, that's the induced map. That's not quite an isomorphism. So I lower star goes from, you can write like this, homology of G invariant form with respect to my D into, well, the Ram cohomology certainly of M, but now the classes are G invariant. And this is an isomorphism. So we are again the G invariant cohomology class are the obvious thing, right? So the Ram cohomology classes. Such that G star alpha is equal to alpha. Right, each diffeomorphism on a manifold induces something in the Ram cohomology. Okay, and in that sense, the cohomology class should be preserved. So cohomology of G invariant forms becomes just the cohomology class which are G invariant. Okay, so let's prove this. Okay, so I have this inclusion here. what do I have to prove? First, let's prove that I star is injective. Well, first, let's make the following observation. I takes closed forms to closed forms. Right? Because, well, it's a subcomplex, right? It's a subcomplex, right? Even not just, I mean, it's even better than also the wedge product. It becomes a subcomplex, which is invariant on the wedge product also. Right? If I take two G-invariant forms, I take the wedge product, that's natural respect to diffeomorphisms, so it's again G-invariant. So in the Ram homology, I have another nice structure, which is given by the wedge product. Right? So this is even an algebra, this is an algebra isomorphism in that sense. Okay, so I takes closed form to closed forms. Of course, so that's what this is. Sorry, I don't need this. Hinz induces a mapping cohomology, right? That's what I mean here. I get a mapping cohomology because it takes closed form to closed forms. And I want to show that I star is injective first. And then I want to show it's onto. So take a G-invariant form. D omega is equal to 0. And assume that the cohomology class of omega is equal to 0. So it means that omega is d eta. And what do I have to show now? So I'm in this complex, right? Here's a form that's 0 in cohomology. I have to show it's 0 in cohomology here, but here I'm only allowed to take G-invariant forms. So I want to show that omega is also d of something that's G-invariant. Well, so now I just observe that G star omega is d of G star eta by naturality. And now I can integrate. So now integral of G star omega d commutes with integration is integral of G star eta over G. But of course, omega is also already invariant. So integral of invariant form, so it's integral of G omega dg. But G has volume 1. Omega doesn't depend on G. So it's just omega. So it means that omega is d of eta prime, where eta prime is G invariant. Here I have the average. That's my invariant form. Okay. So that's injective. But it's onto. Why is I star is onto? So take a cohomology class. So let's take an alpha. A cohomology class, a Ram cohomology class, which is G invariant. But under the induced action on G or G on the Ram cohomology. So this means, right? So G star alpha is equal to alpha. So first I can represent alpha by form. Right? So alpha is the Ram cohomology, or some closed form. Just choose one. Right? And now I want to claim that I can make omega G invariant. So what can I say? Well, first I can say, well, G star alpha is alpha. That's G invariance. G star alpha, well, that's G star of omega. But that's by definition G star of omega. This is how G acts on the Ram cohomology. And now I claim that because I get alpha for all G, that the average of omega, which is again a closed form because omega was closed, average takes closed to closed. So that was this formula I just erased. Which means that if d omega is closed, which is what we have here, right, we chose one which was closed, then d of the average of omega is also closed. And I claim this should be the same de Rham cohomology class of omega or of alpha. And then I would have represented my class alpha by something that's G invariant. Okay. So that would be the claim that the map is onto. So how do I show that? Well, first notice, so we already have it written down here, right? G star omega is the same thing as omega. But this was alpha. That's the same thing as omega. So they lie in the same de Rham cohomology class. So that means the difference is exact. Right? So G star omega minus omega is d of eta. Because this eta might depend on G, but for each G, the difference is exact. Okay. And now can you integrate over G? And that's d. Again, d commutes with the integral over G of eta G, dg. That's my average here. So it's precisely the average of omega. This is independent of G. The volume is 1, so it's omega again. That's d of some eta prime of this eta prime here. In fact, eta prime is again G invariant construction. So indeed they lie in the same cohomology class. Pardon?
It is tricky because what is the dependence of eta sheet with respect to sheet?
I don't care. I don't care.
Well, integral.
Pardon?
Must be integral.
Ah, okay. Okay, I have to say that I can choose eta G, say, depending differentiably on G. Right? Because this depends differentially on G. How do you do that? I certainly have to do. Are there some explicit ways you can do that? Two forms in de Rham cohomology class, you want to write SD as something. I think there's some explicit integrals or something like that. I have to convince myself of that. You're right. This can't be hard. But you can choose a differentially on G. Good point. Okay. So that proves it's onto also. It's projective onto, so I get this kind of isomorphism in de Rham cohomology. Next remark is that, well, if the group G is connected, so that's two propositions. If G is connected, then the de Rham cohomology invariant under G is just a de Rham cohomology. And hence the homology of invariant forms is just the de Rham cohomology of the manifold. And that's simply, well, if G is connected, then the action of G is, every action of G is homotopy to the entity by connecting your element G to the entity, and therefore it acts trivial in homology. So if G is connected, you get an action homology which is trivial, but not in the forms. But then I get this kind of representation of de Rham cohomology by a nice complex. Maybe part B, not going to prove that in general, but maybe only in a special case. So this is A is clear now. We just said Y, right? Acts trivial homology. If G acts freely, then the de-Rank homology of M invariant under G is isomorphic to the de-Rank homology of M mod G. So G invariant de-Rank homology smashes the de-Rank homology of the quotient. Since it acts freely, the quotient is a manifold, so I can talk about de-Rank homology of that manifold. Particularly useful, say, consequence of this fact B over here, so right as a corollary, is that if gamma is a finite group, acting freely on M, then I get a cover, right, a normal cover. And then it says the de-Rank homology of the quotient is the de-Rank homology of upstairs invariant under the action of gamma, invariant under the action of the deck group. I think I mentioned that fact once. So this is a special case of this case right here where the group G is discrete, not just a Lie group. Right? In this case, the proof's a little bit easier if it's discrete. I mean, what you do is you show that on the level of complexes, G invariant forms of M which way around? Goes the other way around. Take a form on M mod gamma that goes into a G invariant form of M just by taking a form down here and taking the pullback. So I take a form of the quotient, I pull it back, and I claim that's G invariant, right? Because what does it mean if I have a cover like this? It means that if I let the group act first and then take the projection, that's the same thing as a projection. So that means that if I take, so now take pi star of omega, that's then G star of pi star omega. That means that pi star omega is G invariant. That's certainly in general, even in this general context here, when I have a Lie group and not just a discrete group, then this is true. But in this case, when I have a finite group acting, so it must be finite because I have to integrate, right? All my results over there depend on integration. And of course, in the next step, I want to say that, well, the cohomology of this is just the G invariant cohomology of M. And the cohomology of this is just the cohomology of the quotient. And this I claim is a bijection here. This is an isomorphism. So clearly it's injective, right? If I take a form, the pullback is 0, the form is 0. Right? If I take a form on M, and it's variant under the deck group, because G is gamma here, right? If I take a form on N, it's variant under the deck group, then I claim that it induces precisely a form downstairs. I can think of the cover form upstairs is the same no matter where I take it here in the tangent space. That means I can define the form downstairs on a set of vectors by simply pulling back to any of its pre-images, evaluate upstairs, and because upstairs is G invariant, I get the same value always. So that means the map is onto. So I get a bijection of these complexes here, which is compatible with the operator of D. And then I use this theorem over here. So that's how I prove the corollary. In this more general situation where I have a Lie group acting freely, I have to regard this projection here as a submersion. and then use some theory of subversion to show that this here is onto also. Okay. Otherwise, injective is clear, but onto is not clear. Okay. By the way, there's a more general theorem like this in algebraic topology. I don't know if you know that. Let me just write it down. Kind of good to know. So what if I take the cohomology of a manifold, of a space, doesn't matter, with respect to some Fiedler coefficients. So let's say I have a normal cover. Right? And let's say the order of the group is equal to P. Then if I take coefficients with respect to Q, this is a cohomology upstairs, M, with respect to ZQ, invariant under gamma, if the GCD between P and Q is equal to 1. So if I take ZQ cohomology, which is relative prime to the order of gamma, I get, again, the same kind of statement that I had over here for a general D group. So that's what it looks like for finite coefficients. So as an example, think, for example, of, say, as SO2n plus 1, and then I divide by Z2 to get the projective spaces. So gamma is in tipple map. Because there's only, say, in this context over there, there's only the Ram cohomology in the top and in the first and top dimension for the sphere. I have to see how my intipple map acts on the top homology. Well, the intipple map preserves or reverses orientation depending on whether n is even or odd. Right? And when n is even, it preserves orientation. If n is odd, it doesn't. So for the no, other way around. So the Ram cohomology for the even dimensional RPN has top dimension 0, and the other one doesn't. Okay. On the other hand, you probably know from topology that RPN has lots of torsion, but it's 2 torsion. It has only 2 torsion, and of course the cover is a 2-fold cover. So when this P and Q are not relatively prime, then you have trouble, then it's false. Okay. So kind of, that's an interesting statement in algebraic topology. Okay. We can now apply this to general to homogeneous spaces. So let's say M is equal to G mod H. So I'm not talking about symmetric spaces yet. I'll come back to that a little bit later. Let's talk about homogeneous space. Then if I look at the G invariant forms on G mod H, then I can use our general principle. I take a form, put it back to your foot point. And so this is, let's say I write my G as H plus P, such that at H of P is contained in P. Then we identify T with the tangent space in the usual fashion. I take a G invariant form, I evaluate on the foot point, and what do I get? So an element, a form on P, so that's got a lambda star of P. But it must be, in order to well defined, it must be invariant under at H. So invariant under H, by which I mean lambda star P, invariant under the adjoint action of H on the tangent space. Okay. And that's clearly an isomorphism. If I have a form on P on the tangent space of my foot point invariant under at H, I push it around onto the whole manifold with a G action, and it's independent of how I push it around because the form is invariant under at H, our general principle. So that means that my de Rham cohomology of a homogeneous space is isomorphic to the cohomology of the following complex. So I take forms on this vector space invariant under H, notice that this is a finite-dimensional vector space. Right? I have an action of H. That's again a finite-dimensional vector space. Okay. And on this I have a differential. So it's the homology of the following differential weighted complex, where D simplifies compared to, say, the general formula for a differential form. It's just, I claim it's something algebraic. Summation omega applied to xi, xj where here in the middle I remove xi, I remove xj. And here I take the component in the direction of h. Where, so here omega is left invariant. Which identify then with an element of this lambda star p. And xi are left invariant also. And then here I have to take the component h because this should be interpreted as, of course, omega is a left invariant form, d omega is again a left invariant form, so interpret as something in this vector space. I apply to left invariant vectors here, and I evaluate at that base point again, and then it becomes an element of this space right here. But the formula I wrote down right here is simply algebraic. Right? This is simply an algebraic formula. I don't have to take any derivatives or anything at all. I just have to look at the Lie bracket and see what the component is. And of course there's a sign, right? So minus 1 to the I plus j.
The xi are on P, right?
Pardon?
Teacher, right? Xi belongs to G.
Belongs to P, sorry. Belongs to P. Yes, I want to define it on the exterior forms on P, right? So the xi's belong to P, not just to G.
How did you cancel the remaining terms?
Pardon?
How did you cancel the derivations? The other terms?
So the other term, what does it look like? It looks like minus 1 to the I, xi, applied to omega, the xi deleted. Right, that's the extra term. Well, the x's are left invariant. The form is left invariant. This function is constant. Differentiate in the direction of xi, I got 0. So this is equal to 0. Since everything is left invariant. Okay. So it is a constant of the usual formula. Because that term is 0, now it becomes completely algebraic. So that's now immediately a consequence of our general theorem. Of course, this differential here in general might be complicated to figure out. Quite as easy as one might think. Particularly, it's interesting, say, if I look at the case of a Lie group. So I got a cohomology of a Lie group in this fashion. Cohomology of G. Simplifies a little bit because I don't have to take any H components here. It's just all the brackets in G. Right? And now this makes sense indeed for any Lie algebra. Right? I don't need a Lie group. So I can call this this object also, say, the cohomology of the Lie algebra. It's called the Lie algebra cohomology, in fact. Right? And now it doesn't matter whether G is compact or not. So in this general setup here, I've implicitly used the fact that G is compact because I used an averaging operator and the consequence of the averaging operator. So this is for compact homogeneous spaces. Now this makes sense for any Lie algebra. So it's called the Lie algebra cohomology. And it's only a cohomology of a Lie group if the Lie group is compact. Otherwise, it's some algebraic object. I don't know if you've seen that before, Lie algebra cohomology. So.
The algebra cohomology for a representation.
Right. Right.
You need that term.
Correct. Correct. Right. Okay, let's see. Now let's apply it to symmetric spaces, I think. Yes. I'll do one application of this, this later on, but right now let's apply it to symmetric spaces. So let's take a symmetric pair. So I have this general setup of a symmetric pair. I take my Cartan decomposition. So for a symmetric pair, it has the following nice fact, that if omega is G invariant, this implies that omega is closed. So every G invariant form is organically closed. So that means this complex here becomes particularly simple. There is no differential. The kernel is everything. So hence I can say, well, the Gram cohomology of a symmetric space is simply equal to isomorphic to this vector space. Invariant under Aristotle position, of course. So I don't have to take a cohomology. I can forget about the differential over there. And this now becomes a representation theory problem to figure out those in this finite dimension vector space of exterior forms on P, what are the elements that are H invariant. So H acts on this vector space here via representation, and what are the vectors fixed under the representation. That's something that one can figure out. B, omega is G invariant if and only if omega is harmonic. So I'll come back to harmonic forms a little bit, but let's first convince ourselves of the first part. Well, it's already on the blackboard. So I'm using this formula here. I can use the theorem here, right? Okay, so I should add here, this is a symmetric sphere of compact type. And hence G is compact. Because that's what I'm using all along. The group G is compact, so I'm looking at a symmetric pair of compact type. Of course, if it's non-compact type, one can show it's just diffeomorphic to Rn, so there is no Durham cohomology. So the compact type is the only interesting case of Durham cohomology of a symmetric space. And then, of course, we have this property of a symmetric space that P comma P is contained in H. This was a characterization of symmetric spaces. Well, now look at this here. Xi and Xj lie in P. And hence this expression xi xjp, H is equal to 0. Now, what am I doing? This of course doesn't make sense. I apply omega to vectors in P. I want the P component, which is what I need right now. I want the H component to be 0. That makes a lot more sense, right? These are in P, they're tangent vectors to my space. I want to interpret these as tangent vectors. And P, the P component of this, is again the tangent vector. Pardon? begin. There we go. So that's it, follows from this proposition. G-invariant forms are harmonic. So I don't know how much you know about harmonic forms. There's a Laplace operator given by d delta as delta d. Delta was plus or minus star d star. It is kind of Laplacian. It has various properties. For example, this now goes on forms, right? On K forms. Laplacian equal to 0, that's called harmonic. That's if and only if d omega is 0 and delta omega is 0. I think here I should assume M compact. So harmonic forms are precisely those that are closed and co-closed. Have you seen this kind of stuff before? Kind of. What's another important property of harmonic forms? In terms of the Durand cohomology?
In each class, there is one and one harmonic representation.
Exactly. So let's see. For any alpha in the Durand cohomology of M, there exists a unique, that's important, omega, which is harmonic. Of course, if it's harmonic, it's closed, so I have a Durand cohomology class. It is a given Durand cohomology class. It's usually called Hodge theory. That's non-trivial. This is not hard. Just apply Stokes to the definition of delta. That's kind of application of Stokes theorem. Very nice application of Stokes theorem. Whereas this one here is more difficult. So that's usually called Hodge theorem. A nice book that does that is Warner's book on manifolds. I forget the full title, manifolds and Lie groups maybe. He also, pardon? Foundations of manifolds and Lie groups. Okay, there you go. So yeah, towards the end of the book, he does completely the Hodge theory in this representation of Durand cohomology plus a harmonic form. He does that. So that's what I need to prove part B. So here I take a G-invariant form. And I want to prove it's harmonic. We already saw that it's closed, so it's a closed form. So look at its cohomology class. Call that alpha. So of course G star alpha is alpha, right? The form is invariant. If the cohomology class is invariant. I now represent alpha by harmonic form. So exists eta harmonic such that cohomology class of eta is equal to alpha. Of course, now if I look at G star of eta, Gx by symmetries, I claim this harmonic again. Since Gx by symmetries. Right, this here, we look at a symmetric pair. Right, we have a metric on this is implicit that Gx by symmetries. G certainly preserves D. We have used it many times. It preserves delta because it respects the metric. So therefore it commutes the star, and then it commutes delta also. And therefore if omega has Laplacian 0, then so does the G star eta. And of course, I know that G star eta, cohomology class of this, is G star cohomology class of eta, and this was alpha, which is a cohomology class of eta itself. Unique harmonic forms now implies that G star eta is equal to eta. Okay. So the harmonic forms are automatically G invariant. Because this implies more generally, right, to any Riemannian manifold. Right? If you have a Riemannian manifold, then harmonic forms are automatically invariant under isometries. Like if one wants to, I can get a different proof that, that invariant forms are closed. I could do the following. Well, so if I have a symmetric space, I have a symmetric pair, then I have symmetries. So for each P in G mod H, I have a symmetry around P. And if omega is invariant under the full isometry group, right, in this context, G is usually assumed just the identity component of the isometry group, not the full one. If it's invariant under the full isometry group, of course, there I have the symmetries in there also. Right? So it would be invariant under symmetries. Well, I claim if that's the case, so if the symmetries pull back a form to itself, this implies very easily that omega is closed and co-closed. How would you do that? What does the symmetry do at the base point? It's not quite true.
Derivative.
Derivative minus identity. Right. So it does something to the K form, multiplies by a sign. Right. So SP star omega at the point P is minus 1 to the K times omega at the point P. Right.
Before is 0 or its derivative.
Said what?
If K was odd, we would have that W is 0. But only
No. Oh, if it's invariant, yes. Correct. That's another. Maybe we'll get back to that. But also, it implies even or it doesn't matter. It implies this right away because the degree of omega and d omega differs by 1. If omega is invariant under this, so is d, because they commute. So both this and this are invariant, but they have different. Their degree differs by 1, so the sign changes by 1. Same thing here. This degree differs by 1, so therefore they must be 0. So it's again my old principle that if I have a tensor of odd order invariant under the symmetry, it must be 0. This is a modified principle. If I have two tensors whose orders differ by 1 and they're both invariant, then this must be 0. Okay. Because it has to be invariant under the full isometry group in order to be invariant under symmetries. And as you said, that if I have that property, then all degrees of odd order are 0. Right. So this here would imply if omega is in omega 2k plus 1m, G invariant, this would imply that omega is equal to 0. Okay. Which then imply that the odd-dimensional de Rham cohomology is equal to 0. Which clearly isn't always the case. Right? Think of odd-dimensional spheres, for example. So this here really is a property that one would have to require, which isn't always true. But just for the fun of it, I mean, this is kind of a cute argument. And I'll come back in a minute to this question: when is the symmetry part of the isometry group, part of the identity group of the isometry, and when not? One can easily decide that. Before I get to that, let me mention one more corollary of this fact here, which is important. So GH symmetric pair, or if omega and eta are harmonic, then the wedge product is harmonic. Right, because what is harmonic for a symmetric space is the same thing as G invariant. But if I take a wedge product, that's G star omega wedge G star eta. So for omega and eta invariant, then the wedge product is also G invariant. And then I use this other direction here to say that M is harmonic. So to start with a harmonic form, it's G invariant. That means the wedge product is G invariant, which means it's harmonic, using both directions. That turns out to be a surprisingly strong property. It's almost never true, but wedge products, harmonic forms are harmonic. Like this property has a name. So such a space where this is true is called geometrically formal. So it's something that's important in rational homotopy theory. So they're formal in the sense of rational homotopy theory, whatever that means. Right? So it's a very strong property of a space. Almost none of the homogeneous space satisfy this property. It's very special for symmetric spaces. Kind of surprising. There was a talk in the seminar about this 2 weeks ago or so, the geometry seminar. Talked about formal spaces and geometrically formal spaces and things like this. There are a number of theorems which says that a given space is not geometrically formal for any metric. So lots of papers on this subject. The only good examples are symmetric spaces. Okay, so that's an important consequence of this fact right here. Okay, last result addresses this issue right here. A special property of symmetric pairs. The following are equivalent. Formulate them in the right order. I want to prove them. The symmetry is contained in G. Remember, you should think of as G as the identical component of the symmetry group. This is not in general true. We saw that over there as consequences. Or equivalently, the symmetry at the base point H is an element of H. Because remember, symmetries at any point could be obtained by symmetries at the base point just by a conjugation with left translation. So if I understand these here, I understand these. And this turns out to be equivalent. B, the odd Betti numbers are 0. Or in other words, the odd Durand cohomology is 0. In fact, we just saw a proof. That was a proof. The Euler characteristic of the manifold is positive. D, the rank of H is equal to the rank of G. And E, the involution, so remember the symmetric pair comes with an involution, it's called a sigma. Sigma is an inner automorphism. Right, by definition, sigma was an automorphism of G whose fixed point set essentially H. This was our setup for symmetric pairs. Sigma is just an automorphism, but it's inner if and only if any of these other properties hold. So all these are equivalent for symmetric spaces. So in particular, these two properties here are, again, topological consequences of a symmetric space. I guess in here I should assume in B and C if it has compact type. Well, actually, no. They're all zero if it doesn't have compact type. Here I have to assume it has compact type. No, not either. Sorry. If it's non-compact type, it's Rn, and the characteristic of Rn is equal to 1. So even there it's true. Because the main interest of this theorem is in the case of compact type. A implies B was the theorem over there, right? So omega I can assume is G invariant, and this implies the omega delta omega is equal to 0 by this argument over there. So this means that the symmetry also keeps omega invariant, because the symmetry lies in G, and it's sufficient to look at G invariant forms to compute the de Rham cohomology. And so then this argument over there implies that if omega is a form of degree 2k plus 1, this implies that omega is dead zero. So it's a G, a zero form. I look at the base point, so I look at the base point. And this implies it's 0 at the base point, but the form is G invariant, so it's 0 everywhere. Okay. And of course, this implies the de Rham cohomology is 0. So it's A implies B, while B implies C. That's clear, right? What's the order characteristic? It's the alternating sum of the Betti numbers. There aren't any odd-dimensional ones, so it's just sum of the even-dimensional Betti numbers. So that's clear. The definition of the order characteristic. C implies D. I need another general proposition. Maybe that's probably the most interesting part. D implies E, it's not so hard, that's easy. But C implies D is a following general statement. It's kind of interesting about homogeneous spaces. Not symmetric spaces, but homogeneous spaces. So I look at homogeneous space G mod H, where G is compact. And this claim is the following, that the order characteristic of G mod H is positive if and only if the rank of G is equal to the rank of H. In fact, there isn't even a stronger statement, which is more difficult to prove, so I just want to mention it. If the rank is even, if the rank is the same, I can even write down a formula for the order characteristic. And it's the order of the Weil group of G G divided by the order of the Weyl group of H. So H is a subgroup of G. They have the same rank. For example, if I want to, I can look at the maximal torus inside H. H and G have the same rank. It's also a maximal torus inside G. Right? And the maximal torus, I have the Weyl group acting, but now I have two Weyl groups acting, one for the group H and one for the group G. Let me look at the order of the Weyl groups. Of course, these are positive, they're non-zero, and that's what the Euler characteristic looks like for homogeneous space. That's more difficult to prove. Let's see which direction do I want to do. Maybe this direction. So rank H is equal to the rank of G. So like is it over here? I look at a T maximal in H. Is an also maximal in G. Okay. Then I can look at the following fibration. I can look at G mod H, no, G mod T goes to G mod H, and the fiber is H mod T. So I claim that's a fibration. I send the coset GT into the coset GH. T is contained in H. That's my map. Do you know a property of Euler characteristic of fibrations?
Behaves like a product.
It's like a product. So the one for G mod T is the one for G mod H times the one for H mod T. So if I want to show that this is positive, it's sufficient to show that these are positive. So that means I've reduced the problem to showing that a Lie group, a compact Lie group G divided by its maximal torus has that property. In fact, I'm going to show more than that. I'm going to show that the odd Watt numbers of G mod T are equal to 0. So it implies the Euler characteristic is positive. For this, I'm going to use my what I proved by the Ram cohomology of G mod T. I can identify. So let's say write G as the maximal torus plus the complement. I can identify this with the forms on P, which are invariant under the maximal torus T. And then I look at the homology of that on the differential we discussed earlier. So it's homogeneous space. I just pull back to the tangent space. I look at that vector space. I have a look at the Eistrup representation. That's now my action of the maximal torus on P. I want to look at invariant forms. And I want to claim that if I look at a form of odd degree, invariant on the torus, it's automatically 0. So even on the form level, I just get 0 for an invariant form of odd degree. And for this, I use the root space decomposition of my the algebra G. And the G was the torus T, direct sum with positive roots of a root space G alpha plus G minus alpha intersected with G. So here, G alpha was in the root space in the complexified Lie algebra. G minus alpha was its dual. So if I take the direct sum plus its conjugate, there's something in the real vector space. These have dimension 2. Root space had dimension 1. So this is complex dimension 2. This has real dimension 2. And T x on these spaces by a rotation given by roots. So essentially e to the I alpha of t. I can view it as a complex two-dimensional vector space, and I know how the torus acts on this and on this here. If I reinterpret the real space, it just acts by rotation. I think at some point we discussed this. So let's say I have a very invariant form on P, right? So P is the sum of root spaces. All these root spaces are two-dimensional, and I want to find a form invariant under an action of the torus, which acts via different rotations in all these two-dimensional spaces. But now I can just say, well, the only invariant forms in this two-dimensional vector space are the zero forms and the two forms. Right, I have R2. I have a group acting by rotations on it. What are the invariant forms? Only the zero form and the two form. So where I take two orthonormal vectors, say, in this vector space, take their wedge product, that's invariant under rotations. And the zero form is, but nothing else. Because now the invariant forms must be wedge products of all these, of this whole decomposition, and therefore it has to have even degree. So all degree ones are zero. So that follows from our general theory. Let me indicate the other direction, because that's a fun direction also. So assume that the rank of H is less than the rank of G. I want to show the Euler characteristic of G mod H is zero. This would be the other direction. To do this, I use another theorem that relates Euler characteristic to vector fields. Do you know what the relationship is? So how can I show that a space has zero Euler characteristic?
You'll find a vector field that
Doesn't vanish, right? So that's the Hopf theorem. If M has a vector field X, with X at P non-zero for all P, this implies the Euler characteristic equal to zero. So that's how we want to do this. We want to find a vector field. And what vector fields do I have on a homogeneous space? Well, I have natural ones, namely action fields. So I want to find a vector X in G such that X star on G mod H is not everywhere non-zero. And that's not so hard. So let's first say, what does it mean that X star vanishes at a point GH? So I have my action field. Remember, I just apply the one parameter group and differentiate. That's how the action field is defined. So this here was ddt of x tx times h at t equals 0. This was the definition. For this to be 0 is the same thing as saying that if I apply left translation to the vector field x star, it's equal to 0. Or being non-zero is the same thing as this being non-zero. Well, so that means that left translation applied to this here must be non-zero, which means I can say that which says that so this is the same thing as saying ddt at t equal to 0 of g inverse x tx gh is equal to 0. Right, so that's conjugation. Right, so this conjugation, I can then say I can put it inside. That's x of Achi times h must be 0. So that's the action field corresponding to AGX. Right now I take the one point this direction, multiply H, differentiate. That's the action field corresponding to this at the foot point H equals 0. But what does that mean? I claim it means that if I look at this conjugate, x, how do I get the valuation at the foot point? I take the component in the direction of p. So I claim this being 0 is the same thing as this lying in H. Right? If this element lies in H, that's the Lie algebra of those action fields that vanish there. Right? Then that's what this means. So my action field X has a 0 somewhere. So X has a 0 somewhere. If there exists a G such that AGX equals 0. So let's interpret that by using the Weyl group. So now we can use the Weyl group again. It's a very nice application of Weyl groups. Because let's look at a maximal torus. So I take a T prime inside H, which is a maximal torus. I can enlarge that to a bigger torus inside G, which is also a maximal torus in G. So I can enlarge my maximal torus. It's bigger. These aren't the same. That's what it means they don't have the same rank. That's when I'm going to start using this. What does this mean here? I can say this is equivalent to saying there exists a G prime in G such that at G prime, at G, X lies in the Lie algebra of T. Because everything in the Lie algebra of H, of T prime, sorry. I want to see when does it lie in the Lie algebra of H. Anything in the Lie algebra of H I can conjugate into its maximal torus. So I can take my vector here, choose a G prime in H, but it doesn't matter. It sits inside G, and conjugate it into T prime. So want to exclude that. That's what a 0 looks like. Right. This is what I don't want. So I don't want this, that some conjugate lies in T prime. But X, I choose X in T. So X and at G prime X both lie in T. And hence, there exists an element of the Weyl group that takes you one to the other. So hence there exists omega in the Weyl group of G such that omega of this at G prime G X is equal to X. And I want to avoid that. Right? So what I do is I choose an X in T. Such that if I apply the whole Weyl group times X, if I look at the union of the Weyl group elements times T prime, such that X does not lie in that, so it's not an element of the space. T prime lies in T, so it's really a subtorus. W is a finite group. I look at all the finite union of these images of these hyperspaces, of these subspaces, and then I certainly an X in there. So that means that this element cannot satisfy this property here, because this says a conjugate of X lies in T prime, not just in T, but in T prime. But this element here is a Weyl group image of X. And I'm choosing my X such that it doesn't lie in any of the Weyl group intervals of the T prime, and that does it. Okay. So it's a nice application of the maximal torus theorem and the Weyl group X on the maximal torus. Okay, that's it. I'll put this stuff on the notes. So on the beginning is in the notes right now. I'll put it in the notes the next couple of weeks when I find time.